Started. All right. So still we are in volumetric analysis, and then that means, can anybody tell me what is volumetric analysis? Very quickly, quick answer. You have to open your mic and tell me. Volumetric analysis that requires to consider the volume of the solvent and solution or the chemicals. So we are still in the volumetric analysis, and then we will see the oxidation and reduction reaction occurring in this solution or in between that solution when we are adding together. All right. So the learning objective for this is we will know how to assign oxidation number to the element and identify which one is oxidant and reductant. So this time at the beginning, let me remind you that there are some terms will be confusing, maybe confusing to you if you do not pay a good attention to it. Mostly oxidant, reductant, and oxidation, reduction. All these four terms are mainly, we will be talking quite much about it. So we will try to remember what is what, and also try to understand actually why we call it oxidant and why we call it oxidation reaction. And we will see that how does oxidation and reduction reaction to be balanced by through the half equation method. Half equation, I will talk about it, why we call it half equation. And also stoichiometric calculation based on this redox reaction. So we have so far seen different type of reactions, right? Single placement, acid-base reaction, precipitation reaction. But now where we come, it will be double displacement reaction. All right. So both time this reaction is happening for the both cases, and it will be oxidation and a reduction reaction. So what is oxidation and reduction reaction? So this red ox, it is coming from reduction and oxidation. All right. So both, I mean, together we call this oxidation reduction reaction is a redox reaction. So redox reaction involves in transfer of electrons. When electrons transfers are involved in the reaction, there will be redox reaction going on. And to remember these two mnemonic we should remember, that is oil and rig, right? Oxidation is a reduction, losing. Oil is OIL, oil, and RIG, rig. So oxidation is losing of electrons and reduction is gaining of electrons. So we should always remember these two mnemonic so that it will be, our life will be much more easier in this case. Otherwise, it is quite confusing. Oxidation is losing of electrons. So oxidation, when some element is losing one electron, or sometimes is donating one electron, it is called the oxidation is happening for that case. All right. And then the opposite thing when happening, it is called the reduction is happening there. But when oxidation is happening there, that is a reductant. Okay. Where the oxidation is happening, that chemical is a reductant or reducing agent. So that's why I was saying that it is a confusing, but if we understand it, it will be very easy. So how do we know that oxidation number is increasing or decreasing? First of all, we have to know the oxidation number. How do we assign the oxidation number, and what does actually oxidation number mean for a chemical for us. So oxidation reaction involves increase in oxidation number. So when oxidation number increases for an element, we call it that oxidation is going on there. Okay, or that element is involved in oxidation reaction, and when it reduces, we call it the reduction is going on. So how do you know that, how do we find out the oxidation number for an element? First of all, we have to look at the molecule. Let's say it is an X and Y or AB. Which one is easier for you to remember? It's a molecule called XY or AB, right? When they are in free state, like sodium chloride, sodium and chloride. Let's say sodium is X here and chloride is Y. That's why I said XY. So if for sodium chloride, when we write, this is, we do not show any charge on them. There is nothing, right? Sodium chloride, nothing there. Sodium hydroxide also, OH. We just write it here like this. We do not write any charge or anything, or any negative, positive sign we don't show, isn't it? So that means in a element, in a molecule, they are together based on their charge neutrality. So the whole molecule, if they have to be stable one, they should be neutral. And they will, those elements in the molecule like sodium, chloride, hydrogen, oxygen, they will arrange in a way that neutralize the opposite charge they are encountering. What does it mean is, when sodium and chloride comes together, sodium has one positive charge and chloride has one negative charge. So that is why sodium and chloride, these positive and negative, cancelled out and they become neutral. Same thing goes, hydroxyl has negative one, sodium has positive. So positive, negative cancelled out, and then sodium hydroxide is zero. There is no charge anymore. No charge. They are carrying no charge, and that is why they are neutral. So they are stable in that sense. What I'm saying that if they need more of the same atoms, like 2 sodium, they need sodium carbonate, Na2CO3, sodium carbonate. So this one, why there's 2 sodium here? Because so each sodium is carrying one charge, one positive charge, but this carbonate is carrying 2 negative charge. So if when the sodium, one sodium comes in close to this carbonate CO3, right? When one sodium comes close to CO3, the CO3 is not neutralized. Still, it has one negative charge on it. And due to this negative charge, this molecule cannot be stable. This molecule cannot be stable. So what it has to do? It has to bring one more positive ion or positive charged element. So it can be hydrogen. Another hydrogen it can bring, and if one hydrogen, this one positive charge, it will bring or add up so that this one and this negative charge will cancel out, or there can be 2 sodium. So this way it will be neutralized. The whole charge of this element will be neutralized, and then they are becoming neutral molecule. All right. So this is what I mean that if they say they will rearrange or sum up or group up in a way that they can neutralize the charge. But now at the beginning, why sodium has to be positive, right? When we look at the element periodic table, we have the periodic table. I think everybody has one already. You know, I told in the first class that you should have one in front of you. So if we look at the periodic table, what do we see? We do not see any charge, no positive, no negative, nothing, just elements: sodium, chlorine, fluorine, iodine, helium, water, oxygen, nitrogen, all are in their respective molecule symbol. There is no positive or negative charge, right? So that is why I say the free element is careful, it's not radical, it's free element. They should always have zero oxidation number. That means if we look at the periodic table, is hydrogen, is sodium, is magnesium, not magnesium, sodium, what is that? For lithium, sodium, potassium, sorry. So lithium, sodium, potassium, all of them has no charge. So all of them are zero. There is no charge in the periodic table. Or calcium, magnesium, zinc, iron, anything. All are zero when they are in the periodic table. That means free element. Free elements are always zero. So in the periodic table, we see that it is zero in free elements. And then ionic compounds. These are the ionic compounds. So far, I was talking about sodium carbonate, sodium chloride, all those things are the ionic compounds, and they should have equal charge on ions. For example, sodium chloride, positive and negative. Aluminium oxide, also 3 positive ion, and oxygen has 2 negative ion. So 3 and 2, how come they become equal? That is why oxygen has to be 3 atoms of oxygen, and aluminium, there are 2 atoms of aluminium. So altogether it becomes positive 6, and here it becomes negative 6, and then they cancelled out each of, both charges are cancelled out. So aluminium oxide is formed. Calcium fluoride, the fluorine is -1, calcium has +1, so that is why 2 fluorine are there. In this way, if we go down, we see that oxygen in compound, oxygen has always 2, but there is exception that superoxides, they have half, and then hydrogen peroxide, they have -1. Oxygen in general has always negative 2 charge, okay, always -2 oxidation number. Only when they are in H2O2, that means hydrogen peroxide, or in the superoxide region, then they will have different charges or different oxidation number. For hydrogen peroxide, it is -1. All right, it is -1. For carbon dioxide, for H2O, nitrogen oxide, so sodium oxide, so all are -2 here. All are -2, and that is why this is hydrogen is +2, oxygen is -2. Sodium is +1 times 2, oxygen is -2. So this way it will be. Hydrogen will always be having +1 in compounds with non-metal. But if they are attached to the group 1 element like lithium, sodium, potassium, all those things, cesium, then only hydrogen will have -1. Otherwise, wherever hydrogen is, it will be +1 charge. Okay. Molecular ions and molecules. The sum of oxidation number is equal to 0 for any molecule, and that is how they become neutral. And magnesium oxide, one example is magnesium oxide, that magnesium tetroxide, and oxygen is -2 because it is not H2O2, so it should be -2. And then if it is -2, 4 times -2 means -8, right? 4 times -2 is -8, and magnesium we do not know how much, so we just consider it X, because altogether they are carrying one negative charge. So this negative charge is going to where? Is magnesium or on oxygen? We do not know. Now let's find out. So I write it here, magnesium oxide and its negative charge. So magnesium, let's say it's, of course it should be positive because oxygen is much more electronegative. So it is negative 2 times 8 charge, 2 times 4, this 4, 2 times this 4. So negative 2 times 4, and magnesium is positive, let's say X, because we do not know how much it will be. So at the total, the sum of total oxidation number should be 0. What I was talking here, that sodium and chloride, it should be 1 plus 1, total is 0. Sodium hydroxide, 1 positive 1, negative 1, 0. Sodium carbonate, positive 2, negative 2, 0. So altogether it should be 0. Positive X, then positive times 2, negative 2 times 4 equal to X. Equal to not X, sorry, equal to negative 1. This negative 1, which it is carrying here. Right? Manganese tetroxide or MnO4, it is carrying one negative charge, so it will be negative 1 charge, 1 negative charge. So if we solve this problem, we'll see that X is equal to positive 7. X is equal to positive 7. So this manganese is having positive 7 charge. Oxidation state of manganese is positive 7. Now there are some examples. It says that find out the oxidation state, oxidation number for nitrogen, hydrogen, and oxygen. Total is 0. Nitric oxide is total is 0. That's why it is not shown, right? Total 0, we usually do not show it because the charge is total charge is 0, which is power 0 means 1. So total charge is 0, and by the same way, nitrogen, we have to find out what is the oxidation state of nitrogen. So we just consider nitrogen is X, right? So hydrogen is always 1. We know hydrogen should be always 1. Oxygen is negative 2 always. Hydrogen always 1 means hydrogen, if it is not with lithium, sodium, and potassium, then it is always 1. Otherwise, it will be negative 1. So since it is not with sodium, it is N, yeah, it is not Na. Nitrogen and sodium, two are different things. This is sodium or natrium, and this is nitrogen. Nitrogen and sodium. Don't be confused. So let's say nitrogen is X. We are considering the oxidation number. Nitrogen is X. And from the same equation, we find nitrogen oxidation state is positive 5. And same goes for this carbonate ion, only the total oxidation number is equal to negative 2. So it will be equal to negative 2 here, unlike this 0. It was 0 here, but it is negative 2. Okay, so difluoroxide oxygen. So oxygen, if we look at the periodic table, fluorine is, this is the periodic table, let's say here, oxygen is here and fluorine is there. So oxygen is fluorine on the right side of oxygen. All right, fluorine on the right side of oxygen, and after this column there are helium, neon, argon, all these inert gases, right? So since inert gas, they are noble gases, they do not have anything to give or take. They are very much inert. They do not take participation. So this is not considered. But so when we do not consider the helium neon argon, we can say that fluorine is the extreme right side on the periodic table and the top of the right column, right side or right hand side on the top. So fluorine should have the highest electronegativity. And yes, fluorine is the most electronegative element, then oxygen, and then chlorine, and then so on. So fluorine is more electronegative, and that is why it will be more negatively charged, more than oxygen. Okay, it should be more electronegative so that it is more than oxygen. I will show you the periodic table in a bit, but yeah, this is. So this is, and the total charge is 0 altogether. So fluorine should have -1 times 2, and oxygen is going to be +2 here. All right, +2. Since both of the electronegative elements are here and almost similar, oxygen doesn't like to be positive, but since fluorine is here, it has to be. They do not stay longer. Okay, so main group elements, group 1 should be sodium, potassium, lithium. This is the rule that sodium, potassium, lithium, they should have +1. The second group, magnesium, beryllium, calcium, they should have +2. And group 13, -3 to +4, +5, and group 17, -1 to +7. And these two groups, or due to this oxidation number, we have so much fun in chemistry. If there was not many of this oxidation number, we would not have that much fun. So far, I was talking about this oxygen and fluorine, right? So now here you can see that fluorine is on the right side of oxygen, and this group is inert group, so they do not care much. Actually, they do not care much, so we can exclude them from any calculation or any consideration. So since fluorine on the right side, most right and top, so oxidation, electronegativity is the highest here. Okay, electronegativity is highest here. It decreases when we go down, and also it decreases when we go left, and also decreases when we go this way. Okay, so this is electronegativity, and then fluorine oxygen relation. Now we see that from 3 till 12, this, all right, we have many, and from here till here, actually, we have the transition metal element, transition metals. The elements are called transition metal. And since they are transition metal, they will have different oxidation state. So each of them can have different multiple oxidation state. 2 + 2, from it can go -7 to +7. It can go to this extreme. So it can show negative oxidation state. It can also show positive oxidation state. And due to this, there are so many colors in the world. Okay, so you can see that titanium here is only a little bit of them, just for the first row. You can see this column we are showing. So for titanium, it is +2 to +5. The oxidation state, it goes from +2 to +5. For manganese, it can go +3 to +7. All right. So in this way, and that is why you can see from this figure that when it has +3, it becomes purple. For vanadium, it is +2 is purple, +3 is green, +4 is blue, and +5 is yellow. So when they have changes in oxidation state, they will show different color. By looking at the different color, we can roughly estimate the oxidation state of that element in the solution or wherever it is. This is it, vanadium dioxide, which has +5 oxidation state and it exhibits yellow color. Vanadium oxide, that is +4, it shows blue color, and so on, green and purple. So this thing is actually in the real life. We can do it in the lab. We can see it. The same thing, vanadium, the same vanadium element, we are taking a different solution or different oxidation state, and it is changing color. You don't have to take it all different 4 beakers. You can take it in 1 beaker and do some mechanisms, some reaction, whether it changes its oxidation state, and along the changes of this oxidation state, it also changes its color. And this is amazing. If you have a chance to look at it, it will be so, I mean, it's quite magic actually. Oxidation number and nomenclature. This oxidation number not only governs the color, it also gives us a fair understanding, or it helps us to remember what is the name of the compound. Compound means when 2 or more than 2 elements are together to form a compound, when more than 1 elements are in a molecule. So this molecule we see iron and chlorine. This molecule is iron and chlorine also. There are 2 chlorine here, there's 3 chlorines here. Right? Same thing. So this is iron 2 chloride and this is iron 3 chloride. And because of this, they will have different color. All right, the same thing, iron and chlorine, but only the number of chlorine are different. So one will have a greenish color, green, yeah. Another one will have rusty color, colorless. Sorry, iron chloride is colorless probably. Iron chloride 3 is greenish probably. So due to this color, oxidation state difference. And mercury oxide, this is mercury 1 oxide because all of them are having 1 oxidation state, number. Mercury, there are 2 mercury, each of them are having 1 positive, and this is oxygen or iodine, each of them are having 1 negative, 1 positive and 1 negative. So 2 times 1, 2 times. So this is 1 oxidation state, right? And that is why it takes the 1. But for this case, mercury and 2 iodine is there. So that means 2 iodine means 2 negative charge. Mercury 1 is there. So 1 means 2 positive charge. So positive and negative, and that is why it is 2 mercury 2 iodide. Lead oxide, again, lead is positive 2 and oxygen is negative 2. So that is why it is lead 2 oxide. So these 2 are different, right? We understand that these 2 are different. Here, although there are 2 atoms, but each of them are carrying 1 positive charge. Here, one atom, each of them are carrying 2 positive and negative charge. For this case, though, lead oxide, right, is lead, oxygen is of course negative 2, and there are 2 oxygens, so it should be 4 negative -4, isn't it? It's -4. So how much iodine, I mean, lead should be there? I mean, charge should be there to make it neutralize. Of course, it should be 4, +4. So each lead, I mean, Pb is plumbum or lead. I'm calling it lead. That means I am used to it. Some people call it plumbum, but I am used to it to call it lead, Pb. So lead is carrying 4 positive charge on it, whereas oxygen is carrying 2 each. There are 2 oxygen atoms here, each is carrying 2 negative charge. So that is why lead 4 oxide, right? So these two again will be different in their reaction and of course in their physical appearance because of this oxidation state. This redox reaction, as I said, that the color changes, one of the example is the firework. All the firework that we see, the color changes, green, yellow, blue, black, whatever. So this nothing but the oxidation state change. And first of all, the reaction is happening, and in that reaction, the oxidation state of that particular molecule is changing. They are burning in the burning, of course, they need to be burned, and then with that heat, in presence of heat, they are changing the oxidation state. For example, magnesium atom loses 2 electrons to become magnesium ion. All right. So when there is magnesium and oxygen all together in the reaction, and oxygen then takes up these 2 electron because oxygen is electronegative. That means it attracts electron. Electronegative means it attracts, it takes electron. Okay, so oxygen will look for that 2 electrons and then it will take up that electron. All right, so in this case, magnesium, when it is losing or giving up 2 electrons, it is oxidation reaction is happening. And for reduction, all right, and for oxygen, after taking up the 2 electrons, the reduction is happening because it's gained the electron. So magnesium burned with an intense bright white light, actually very bright and white light magnesium. The white light you see is magnesium actually, and produce a very white light because of this the oxidation reduction reaction that goes on in the molecule. Now, oxidant and reductant. Since we already are comfortable with the oxidation and reduction, right? Oxidation is losing of electron, right? Oxidation is losing of electron. That means if some element is losing some electron, its oxidation is happening. Another one which is taking up the electron, the reduction is happening. Now, oxidant and reductant, or also this oxidant sometimes is referred to oxidizing agent. Oxidizing agent. Okay, and this is a reducing agent. Reductant is a reducing agent. Oxidant is the reactant that undergoes reduction. Does it make a little bit uncomfortable now? Oxidant is the reactant that undergoes reduction. So when there is an oxidation reduction, oxidation reaction is going on, actually reductant is there, so that the oxidation is going on, and the reductant where there is the oxidation reaction is going on. All right. Okay, so oxidizing agent will reduce someone. All right, oxidizing agent will cause someone to be reduced. Okay, so now oxidant experience decrease in oxidation number. So oxidant experiences the decrease in oxidation number. So in that case, what is the previously we saw it, where does it, here is it, no, here. So if the oxidation number is reducing, so actually what is going on there is a reduction is going on. If the oxidation number is reducing, decrease in oxidation number, so the reduction is going on, and then this is telling us that oxidant will cause this thing. Oxidant will decrease the oxidation number. That means a reduction reaction is going on there. And the opposite is true. So we need to take some time and understand or be comfortable with that. Oxidation and reduction reaction, oil rig, oxidation is losing of electrons and reduction is gaining of electron. But when oxidation is happening, it is happening, but someone else is facilitating for to occur or happen. So a reductant is actually helping for the oxidation reaction to go on. All right. So we need to be careful in realizing these things. Oxidation reduction and oxidant and reductant thing. Now, if we try to understand or identify oxidant and reductant reaction for this reaction, that magnesium and oxygen, start with the easy one that we already have seen it. So magnesium and oxygen reaction is happening and magnesium oxide is formed. So now previously, what was the oxidation state of magnesium and oxygen? Can anybody tell me? What was the oxidation state for magnesium and oxygen before on the left side, that means the reactant side?
Magnesium is +2, right?
Okay. For oxygen?
-1, I guess.
Okay. -1 and +2. Anybody wants to try? Anyone else wants to try?
Magnesium is +2, oxygen is still -2.
All right, +2 and -2. I'm talking about this side, okay? Not this side. Not this side. I'm talking about the left side. So anybody else wants to support your friends or differ from your friends? On left side, magnesium is 0, oxygen is 0. The oxidation state. Remember on the chart, just now we saw the chart, right? The free element are always 0 oxidation state. It does not matter that there is 2 in front here. That's why you think that it is changed. No, it does not change. It's still the free element. It is still at its free form. It did not. Magnesium and oxygen is still, they are free, and then they are wandering, they are free. They did not still undergo for reaction. So they are 0 positive charge. And oxygen is also zero charge, so not positive, zero charge. Oxygen is also zero charge, no negative. But when it goes and form magnesium oxide, now what happens? Now it is, oxygen is very much electronegative, so it took the electron, and magnesium is metal, so metal always try to donate electron. Metals are very generous, all right? So they want to donate electrons. So magnesium donated or released 2 electron to oxygen, therefore oxygen becomes negative 2 and magnesium becomes positive 2. That means it donates 2 electron and oxygen took 2 electrons. Now you tell me what is happening. Here it is oxidation or reduction, or here it is oxidation and reduction. Which one is happening? Magnesium, it released 2 electron or lost 2 electron. So oil rig, OIL, oxidation is losing, right? So oxidation is happening here. Magnesium goes under oxidation, and oxygen, oh, I should draw in another way, right? It's confusing, but you understand that oxygen, when it gains the electron, it falls under this category, rig. Reduction is gaining of electron. Oxygen gained these 2 electron, so reduction occurs there. Reduction occurs there. So that is how it is shown. Okay. All right. So here oxygen is undergoing a reduction because it's taking up electron, and magnesium is going out oxidation. That means it is losing electron. Since oxygen is undergoing a reduction, it is an oxidant because it caused the reduction. All right, oxidant, it undergoes reduction. That means it is an oxidant. But for this case, magnesium undergoes oxidation, so it reductant. Magnesium caused this oxygen to gain, that means to undergo reduction, and oxygen caused this magnesium to lose the electron, so to undergo oxidation. That is why it is an oxidant, it is a reductant. Is this okay? Hopefully. Now write the balanced ionic equation using half equation method. Why do we call it half equation method? Because we will not write the full equation. We will be only considering the part of the reaction where actually something is going on. Something is going on means what? The oxidation and reduction. That means electron transfer is going on, or they are changing from one state to another state. Oxidation reduction is going on. That one we will only concentrate on that part, not on the full part. There can be many other things that is happening in the reaction, or some other elements are involved, but probably they are not doing any reaction. They are not taking part in the reaction. That is why we will not be considering. So only half of this, or part of this reaction, we will be considering. That's why it was the half equation. So the simple one, magnesium and oxygen, how it is happening. Nitrate ion, when it formed dinitrogen oxide, and chromate ion when it forms the chromium or chromate ion in acidic condition. Why this acidic condition we have to mention? It is important. If I forget to mention, please remind me. So balance, there are some rules for balancing the equation, for half equation actually. We will balance all the atoms First of all, we will balance all the atoms. Atoms means this magnesium. There are 2 oxygen atoms. Okay, so we will balance all the elements except hydrogen and oxygen. And when there is oxygen, if there is in the molecule there is oxygen, we will produce or we will counter H2O, that means water molecule, to balance out this oxygen. And then we will balance hydrogen using hydrogen ion in the acidic condition. If there is acidic condition, it says, now I'm telling you, if it is said acidic condition, that means acidic means the solution that able to donate hydrogen ion, isn't it? That able to donate hydrogen ion, that is acidic solution. So acidic medium means we should not have any deficiency or any shortage of hydrogen ion. We should have enough hydrogen ion in the acidic medium. We do not have to bother about hydrogen ion in the acidic medium. All right. So hydrogen we should balance with this hydrogen ion in the acidic medium, acidic condition. Alkali condition, hydroxyl ion. If it is said that in the alkali condition, we should consider, because in the alkali condition, there should be generally should be more hydroxyl ion. So we should balance out using this hydroxyl ion to produce water or produce anything else. We do not have to provide this hydroxyl ion through some reactant. If it is says that in a acidic condition or alkali condition, we immediately understand that even though it does not, we do not see the hydroxyl ion or hydrogen ion in the solution, but since it is in the solution is acidic or basic, we have enough hydrogen or hydroxyl ion in the solution. Question number 4, rule number 4, it says that balance the charge using electrons. Each electron carries -1 charge. Okay, this means -1. 1 electron means 1 negative charge. So if we have enough, after we have balanced out all the atoms and the hydrogen ion and oxygen ion, hydrogen ion and oxygen molecules, all right, atoms, so that after that we have to balance the electrons or the charge. How many total charge should be same on the reactant side and on the product side. That means on the reactant side it is left and right. So reactant side, okay. R means is confusing again. What do I do? This is reactant side on the left side and this is product side. So on the product and reactant side, A plus B, right? It will C plus D, let's say. So the charge -1 should be +1 +1. So negative positive should balance out each other. Also the number of atoms should be same on the both sides. So this is what I say, that charge should be balanced as well. Now for magnesium, number 1, magnesium produces the magnesium ion. First of all, how does it produce? Magnesium is producing 2 magnesium ion, and then when it is producing 2 positive ion, that means what happens? It lost 2 electron, right? Electron lost means it becomes positive. So what is the 2 electrons? Here we have to show these 2 electrons here. Positive, 2 positive, negative charge, 2 electrons. Oxygen is producing 2 oxides, and then there are these 2 electron. Since there are 2 here, there should be 2, because we cannot write in this way. That is incorrect. So two oxygen ion are being generated, each of them having two negative charge, means each of them are taken up two electrons. These two electrons, it has taken up by each of these oxygen atom, but there are two oxygen atoms. So where can we find two electrons from here, right? So these two has to come from this magnesium as well. So we have to multiply this magnesium, then only I will have 4 electron that will balance my need. So this is how we will find out. So magnesium is 2 electrons, 4 electrons, and come on, where is it? Okay, so yeah, so magnesium, that's why I should have to multiply these two, magnesium 2, and it will be 2 magnesium here and 4 electrons here, and then when I add it up together, magnesium plus oxygen, so that it becomes magnesium oxide. Okay, 2 magnesium oxide. So this is how it is balanced both sides. Nitrate ion becomes dinitrogen oxide in acidic condition. In acidic condition means there are plenty of hydrogen ion in the acidic condition. So nitrate ion, when it is dissociating, what will happen is this, how do you balance it? We will produce 2 nitrogen here, and this oxygen that is broken up from here, because here we got only 1 oxygen, whereas we have 3 here. Whereas we have 3 here, we have one oxygen on that side atom, but we have 3 here this side, isn't it? So where does that 2 other oxygen atom goes? 2 other oxygen atoms should produce 2 other water molecule. 2 water molecule should produce, because according to the rule that we have seen, oxygen atom should be balanced by producing water molecule. So these 2 oxygen should produce 2 water molecules. Now this nitrate ion, all right, it is not only producing 2 oxygen, because this N2O on the right side or product side, we see that they have been changed in the arrangement, and here there is 2 nitrogen. That means we have to have 2 nitrogen on the reactant side as well. But if we take 2 here, that means we are having 6 oxygen already, because 3 atoms in each NO3. NO3 means 3 oxygen atoms for 1. So if we add 2, that means 6 oxygen atoms here, right? If we use 6 oxygen atoms and only 1 of them have been used here, so other 5 should have produced 5 water, because 1 oxygen produces 1 oxygen atom. 1 water molecule. 1 oxygen produces 1. Now, these ions, this ion, I haven't balanced it. Now, probably we have balanced the atoms, that 2 nitrogen, 6 oxygen, so 2 nitrogen and 5 plus 1 to 6 oxygen. But this ion has not been balanced. To produce this 5 water, we have to have 10 hydrogen. we have to have 10 hydrogen, and it is an aqueous medium, so 10 hydrogen shouldn't be any problem. But only the thing is we have to consider the charge of the hydrogen. The 10 hydrogen that we have taken from the acidic condition, it having 10 electron, 10 charge, positive charge, along with this 10 hydrogen. We cannot just take the hydrogen, the 10 charge, positively charged, is also coming along. To balance this 10 electron, we already have 2 electrons here, right? 2 negative charge here. So we have already 2 electron here, but another 8 electrons we have to add up. We have to add up on the left side another 8 electrons so that it is balanced now. So that 2 electron plus 8 makes 10 positive electron. And that is how you will see that everywhere it is also balanced. On the both sides it should be balanced as well. All right. Now I understand that please go to menti.com. All right, please go to menti.com and then use the code 3678 36784429. All right, so vote, please vote. I want everyone to vote, and by this time I go and make some tea. Which one is having oxidation? Please vote faster. 2 minutes, yeah? I should show, right? So you can see the slide, and please vote faster. Only 4 of us has voted. I want everybody to vote. How many of us are here? We are quite many of us. All of us are here actually. 12 of us. So please vote all 12 of us. 9 faster. 1 minute. Faster, another 2. "30 seconds, another 2 who didn't vote." "10 seconds. That means that. Okay, so now how do I show the result? So 4 of us has voted for sodium, 3 of us voted for iodine, 3 for sodium, sulfur. Right. Good. How do I remove it? Yes, show the image. Now I know. So for here you see sodium thiosulfate and iodine was 0 at this side. Iodine was 0 this side, right? For iodine in this side, sodium, sulfur, oxygen, all of them were somehow it was positive or negative charge because they were in a compound. But iodine was not in a compound. Iodine was free here. So since it is free, it was 0. It did not carry any charge. It was 0 in the free state. But when sodium and iodine becomes together, that means sodium becomes positive. Sodium is always positive 1, and iodine should be negative 1 that time. So from 0 to negative 1, right? So here it loses electron. Iodine lost electron or give away electron. So oxidation is losing. Iodine is going through oxidation because it's a reducing agent. Okay, so iodine is having the oxidation is happening here for this case. Okay, so now go back to our lecture. It's almost time, but we have to finish it. Now we were here. Okay, so okay, now here we were here, solve the problem and going to the another problem, that is the chromate ion, chromium oxygen. The reaction is asking me to show the reaction. It is asking me to show the reaction of from here to produce here. What are the other things produced? We do not know. Okay, only from here to here. But although on the right side or the product side, it does not show me anything about oxygen related, But I understand that I have to balance the equation, and that is why I have to show this oxygen had been used up or do something. I cannot just say, okay, from 2 chromium, I make 1 chromium 3 plus and that is done. No, I have to consider this oxygen as well because it was in the reactant side. So if in the, let's say, in a juicer, you put something, right? You put mango, you put kiwi, and you put onion as well. So do you only expect that mango and kiwi will come out, no onion? It does not work that way. Whatever you put, it should come out. So that is the same thing. We have to consider this oxygen being used up or being produced some type of product. So we have to consider that one. And that is why this chromium from Cr2, it produces Cr3 plus, which is a lost electron because it loses electron, right? Positive means electron is gone from here, and that is why it becomes positive. So from here, the two electrons are lost, and then chromium is being produced. And we do not have to multiply this thing anything because there are 2 chromium here. There are 2 chromium here as well. So we do not have to multiply by any other factors. Is really, it is okay now. It is quite balanced. But this way we have 7 oxygen atoms. 7 oxygen atoms. So 7 oxygen. Remember that first of all, we should balance out the number of atoms. Second thing, oxygen or hydrogen. Third is the charge. So we will not bother about the charge right now. We will balance it later. So chromium, from there we see that 2 chromium already here. Just write it because we do not consider the charge now at this stage. It will come the later stage. And then this 7 oxygen, how many water it can produce? 7 molecules of water. To produce 7 molecules of water, we have to add 14 atoms of hydrogen. 7 times 2, 14 atoms of hydrogen. Right. So 14 hydrogen, which I added, should be 14 hydrogen plus. Right. So chromium and chromatation, actually, dichromation. So when in presence of 14 hydrogen, because to produce 7 molecules of water, I need 14 hydrogen ion. I just added up. Where did I bring it from? In acidic conditions, so I do not have to bother where it comes from. It is an acidic condition. So 14, 140, 1040, whatever number of hydrogen I need, the acidic condition should be able to provide me. So the 14 hydrogen at ions, it is we just added. I don't have to bother about the source. So this thing added, and then now I see that the atoms, all the atoms are cleared. It's all balanced. 2 chromium here, 7 oxygen here, 14 hydrogen here, 2 chromium, 7 oxygen here, and 7 times 2, 14 hydrogen is there. So should be okay, no problem. The atoms are cleared. Now we have to think about the charges. Left side, I have 2 negative charge and 14 positive charge. 2 negative charge, 2 electron negative, and 14 positive. I cannot write E. I have to write like 14 positive charge. All right, 14 positive charge. On the right side, I see that we have 3 positive times 2, so 6. 6 positive on the right side, right? So how many atoms, charge should I be adding to the left side? Which one is deficient? I have 14 positive here, minus 2, that is 12. 14 minus 2 is 12. And here is 6 positive, 12 positive, right? 12 positive, negative minus positive, so 12. And then here is 6 positive charge on this side. If I bring this 6 to this side, then it will be added up. So I should add another 6 electron on this side, right? On this side, so that it becomes neutral, or it becomes balanced, because this 6 electron and this positive side, if I bring to this side, it will be negative, or if I bring to that side, it will be positive 12. So positive 12 on right side and positive on left side should be okay. So 14 hydrogen, I just need to add another 6 and it becomes positive. Example 3 says the overall ionic equation. When a pale green solution containing iron 2 is mixed with a purple colored solution of manganate ion, actually MnO4 is manganate ions, the purple color disappears. Why does it disappear? Because the purple is not MnO4, is the same oxidation state anymore. It becomes MnO2 plus. It is not the same oxidation state. That's why the color disappears. And from green, it becomes red. Iron becomes red because it is 3 positive charge here. Here is 2 positive charge. So the charge difference or oxidation state different. The color of the solution of the chemical is also different. Write a balanced overall ionic equation for this reaction using half equation method in an acidic condition again. So iron and manganate ion both together. We added. So iron, because it says that Fe3 plus is formed, Fe3 plus is formed, and manganese ion is formed as well. Manganese ion is formed as well. So now, what else is we have to do? Because there are 4 oxygen here, and it's almost, we don't have to multiply or anything. It's almost okay. Just need to balance the oxygen. Since there are 4 oxygen here, I have to add, I can make 4 water molecule out of 4 oxygen, and that is why I have to add 4 hydrogen there. So I just added 4 hydrogen atoms there, or ions there, sorry, and then it almost okay. Just need to balance the charge, because there's 2 positive charge, here's 3 and 1 electron, so that I have to add 8 hydrogen. Altogether I have to find 5 electrons also on the left side. Then the whole thing is balanced, right? The whole thing is balanced just by adding 5 electrons. So balance the number of electrons I have to find out. We see that iron is donating 1 electron because it becomes positive. So that 5 electrons I have to find. This 5 electron should come from here. Unlike the acidic condition, I don't have to consider about how many hydrogen we have to take, right? I said whatever number of hydrogen you can take, but electrons should come from either of these reactants. So you have to count the electron, or you have to keep track of the electron, where it is coming from. Since I need 5 electrons here, I have this electron. I have to have this electron from this reactant, this 5 iron. So 1 iron 2 plus gives 1 electron. I have to take 5 electrons, so I have to have 5 iron plus, so that it will give me 5 electrons. Right? I'll have the 5 electrons here. So this is how we will be, the reaction will be balanced. And later on the either side, these 5 electrons, we can remove it because this is the common on the both cases, on the both sides. So the overall ionic reaction will be like only the atoms or ions, number of different ions are there. All right. So the electrons are on the both sides is same. They are not doing anything. They are just on the both sides. They are same. So they are not changes. We don't need to mention it, and that's why it is removed from the or cancelled out from the equation shown. So now we were in the volumetric analysis. We have seen the acid base. Just now we saw the redox. Next time we'll see the chromatography next week. But before we finish, we'll have to wrap up with this, that redox titration. There is something called redox. We have seen the acid-base titration. This week you are making the acid-base titration. Next, this week you are going to submit the acid-base titration, the report. Next week, this week, Thursday, I will go to the lab 9 a.m. I will still show the titration, acid-base titration. So beside acid-base titration, we have redox titration as well. Okay, we have also redox titration. And why do we need the redox titration? Well, redox titration, due to this electron transfer of this redox titration, since electron is involved here, the transfer of electrons, so the electricity, right? So it can produce electricity, although it's a very minimal, but it produces, and since it can changes the electricity or electrical voltage to some extent by producing the electrons, it can we can use this system to detect a trace amount of ethanol or sulfur dioxide, vitamin C, hydrogen peroxide. All those things we can be determined, or determined is detected, sorry, trace amount of those can be detected in a very trace amount. Okay, it can be detected in a trace amount, and for this case we do not need any what do you call it, indicator. We don't need any indicator because it is signaling us through this electron or electricity difference, electron differences, and it will give there will be a meter or instrument that will read that voltage difference, and it will tell us where this reaction is finishing or stopping or being neutralized. Based on that, it is this type of reaction helps a lot in determining a traces amount in our industries or drink driving, under those things, to prevent the crime or many things. All right, how does it occur? So hydrogen peroxide, it is hydrogen peroxide. It is a very good disinfectant, but also very problematic for human health. So if we want to determine or detect hydrogen peroxide in some solution or in some environment, we can do so by using this magnesium oxide and tetroxide. How do we do it? Because magnesium tetroxide, 25 milliliter of potassium permanganate solution will be used, right? will be used by 20 milliliter hydrogen peroxide solution. What is the concentration of hydrogen peroxide? We can find out the concentration of hydrogen peroxide by this way. So the reaction goes by doing the equation and solving it in the acidic condition as well. So hydrogen peroxide, potassium permanganate, all those things doing the reaction. Magnesium, from here we see that the oxidation state is +7 for manganese tetroxide. It is from +7, it is reducing to +4. Okay, so it undergoes a reduction. It's reducing from +7 to +2, so it's reducing from higher to lower number. So it is a reduction is going on. That is why it is an oxidant. It is causing other to have the oxidation. Whom it is causing to have oxidation? This hydrogen peroxide. Hydrogen peroxide, it is -1. The what do you call it? Oxidation number for oxygen is -1, not -2. All right, it is not -2. Hydrogen peroxide is an exception, so it is a -1, and it is producing oxygen, which is 0. It is elemental oxygen. So this is 0 because it's free elemental. I mean molecule. It's a free molecule and it's 0. So what about this hydrogen, the leftover hydrogen? The 5 hydrogen should produce a water molecule as well. So this 5 hydrogen, and then all together it is producing 8 water molecules, right? So hydrogen, if we see that the number of what do you call it, charge, here it is +1, here it is +1 as well, and here also it is +1, because here oxygen is -2, because it's oxygen, I mean water. In water it is not an exception, it is not hydrogen peroxide, so it is -2. Oxygen is -2, usual oxidation state. But for hydrogen, all over it is +1, whether it is hydrogen peroxide, whether it is hydrogen, whether it is water, all over it is +1, and that is why it does not change, or it does not no significant changes occurs here for hydrogen. So it is an spectator ion. It does not go for any oxidation or reduction reaction. It's just watching. It's just witnessing. It does not do anything. That's why it is a spectator ion. It does not take part in the reaction. So if we do the oxidation reduction reaction and balance out the oxidation, I mean the reaction, 2 manganese oxide and 5 hydrogen peroxide is needed for this oxidation reaction to fully balance out. From there we can just use the N1V1 or C1V1 and C2V2 reaction, where the number of moles is 2 here and hydrogen peroxide is 5 here, right? 5 moles of hydrogen peroxide reacted with 2 moles of manganese tetroxide, and then they produces 2 manganese 8 oxygen water to 5 oxygen as well. So from there N1 V1 N2 V2 we can find out that concentration of hydrogen peroxide was 6.25 times 10⁻² molar, or mole per liter, N equal to C into V. From that equation we find. Why do we have to divide by this? To find out the unique number of moles. This is the stoichiometric ratio, 2:5, so we have to divide by this 2 to get the per unit number of moles, and also hydrogen peroxide per unit hydrogen peroxide is reacting. All right, okay. We're going to finish soon. So if you have any question, please ask now or later, no problem. Another example, that 10 milliliter sample of white wine was placed in a volumetric flask and water was added to make 100 milliliter of the solution. So again, it is 10 milliliter of wine was diluted to 100 milliliter. That means 10 times dilution, 10x. 10 times dilution was done. Then 20 milliliter aliquot of that diluted, okay, from this 10 times diluted solution, 20 milliliter of it was then taken and then titrated against 0.1 molar of acidified potassium dichromate. 0.1 molar of acidified potassium dichromate solution. Potassium dichromate solution was added. And the mean titer was 26.61. All right, 26.61 milliliter was required. So from here we understand that N equals C into V, right? N equals C into V. So from here we will find the number of moles, 0.1 molar and 26 milliliter. Well, of course, we have to convert it to liter. That means we should divide by 1000 to get the liter. So N equals C into V, number of moles, we'll find. It is asking us to calculate the concentration of ethanol in the sample of white wine. What is the concentration of ethanol in the sample? Is almost similar to what is the concentration of acetic acid or ethanoic acid in the vinegar, something like that. So this is the same thing. 10 milliliter of this was taken and then it was diluted to produce 100 milliliter, which is then 10 times diluted, and then from here I took this 20 milliliter. This 20 milliliter was taken from here. And then it was diluted, it was titrated against, and then it produces this with the potassium dichromate. It was titrated and then it produces the greenish green color solution because the oxidation number changes from +6 to +3. So this is the reaction is occurring, and to balance the reaction we have 2 potassium dichromate, 3 ethanol, which is producing 2 and 4, but it is not relevant for us. So we know that is 3:2 reaction, 2 moles of potassium dichromate reacting with 3 moles. We have to balance the reaction first. We have to balance the reaction. This is the most important thing. Since we balance the equation and then number of moles, N equals C into V, from there number of moles of chromate, we found it already. And then number of moles is 3:2, right? It's 3:2. And from there the number of moles, we find the ethanol should be 0.003692 moles. All right. Okay. Now, from there we find it is in 20 milliliter of the ethanol was taken. Ethanol was taken 20 milliliters. So again, from this, using the same equation or same formula to find the concentration, C equals N over V. Using the same formula, we find the concentration, but it was 10 times dilution, so multiplied by 10 or 100 over 10, same thing, right? So we find the concentration of ethanol in that wine sample. So it will be 1.85 molar of the wine sample. Okay. Any question? Ethanol percentage, volume by volume. So we find that 1.85 molar of ethanol was in the solution, right? On the solution. And why do we express it 1.85. Let me tell you quickly, 1.3 significant figures, because in the question it is 10 milliliter, 0.0, 20.0, 100.0, 24.61. There are different types, right? Here also 3 significant figure. This is 4 significant figure. This is 3 significant figure. This is 3. So this is a 4 significant figure as well. So there are 3 and 4 both, but 3 is smaller than 4. So we will follow the smallest significant figures. That is why it is 1.85, 3 significant figures given. Now, percent of ethanol, volume by volume percentage. So 1.85 mole per liter of ethanol, we will just find out the gram. First of all, we will find the gram, because from molarity we change to gram per mass of the ethanol, and then the volume we will divide. So we find it 85 gram, 1.85 moles of ethanol is 85 grams, and then we divide by this density, right? 789, density is 789 of ethanol, milligram per liter or gram per cubic meter. So 789, and then we'll find the milliliter actually. So milliliter over 1000 milliliter, that means 1 liter times 100%, it is 10.78 volume by volume percentage. So from 1.85, right, 1.85 molar of ethanol, we find out the number of mass of that ethanol, and then from that mass we convert it to milliliter, that is divided by the density, all right, divided by the density. The density is not given here, but we can find it from online or from the internet or from any other books. And from there, it is in 1 liter of beverage, right? So that amount of milliliter in 1 liter of beverage times 100%. So we find the volume of volume percentage. The breath analyzer. Usually, if somebody drink and drive, the police will stop and they will check with this alcohol sensor or this type of breath analyzer to find out the concentration of ethanol, certain type of ethanol. If it is more than in your blood, it causes a lot of road accident and all those fatalities due to this drink and drive. And also this alcohol causes a lot of problem to our brain and liver as well. Now our research came out that even a small percentage of alcohol also causes adversely to our brain and liver. So how does the breath analyzer works? It has a electrochemical sensor, so electrochemical fuel cell actually, and it has anode and cathode. What is anode and what is cathode we will see later on, probably if we study electrochemistry. So at anode, this electron is being produced, all right? So oxidation is happening at the anode, and electron is being produced. And at cathode, since let's say this is an anode and this is a cathode, right? So when we put the alcohol inside, or sorry, not the alcohol, when we took the breath, and in the breath or in our breath, the alcohol presence is there. So electrons are going into this, and this breath is difficult to draw this simply, yeah. So when our breath is coming in contact with this anode, the electrons are being produced from here. This electron is being taken up by this cathode. When it's taken up by this cathode, then only the circuit is becoming closed or circuit becoming contacted. The circuit is contacted by this way. So it gives a reading, depends on how much electron it produces or how many electron it is can absorb. Based on that, it produces, and based on the electron production, so we know that the concentration of ethanol is there, right? So if we know that how many electrons are being produced here, for one molecule of ethanol producing 4 electrons. So if I have 100 molecules or 1 Avogadro's number, will have 4 Avogadro's number of electrons here, and depends on that, the more higher current will be produced, and then the reading will go high up, and that is how we know that these people or this driver is under the influence of alcohol, and the police will summon him or give him the fine, and it's rightly so. All right, so this is it for today. Anyone has any question? Anyone has any question?
No, sir.
Okay, thank you. Brian, you said that I thought iodine gain electron. Is it?
That is for the Menti question, sir.
Oh, okay. Thank you for bringing it up. Let me go and check. So actually, what was the question? Which one is having oxidation?
Yes, that is the question.
Oxidation is losing of electron, and it should be sodium, yeah? Sorry. So those who are, how many of you has said sodium? 4 of you. So yeah, thank you very much. Those have taken that. So for sodium is losing the electrons, so that means it is having the oxidation. Oh my God, I confused myself. Right, so thank you very much for correcting it, and that shows that you understood actually.